Welcome to the deep dive. Today, we're really cutting through the noise and diving headfirst into a topic that's just, well, revolutionized how developers build, ship, and run applications. Docker.
Absolutely. It's huge.
And even if you're not a developer yourself, honestly, the core ideas we're going to explore are incredibly powerful for understanding, the backbone of pretty much all modern software today. You handed us this really comprehensive Docker cheat sheet. It looks specifically tailored for Java development, which is great.
Focused, yeah.
So our mission today is basically to pull out the most important nuggets of knowledge from all of these commands and configs. We're not just going to list them off, right?
No.
We're going to help you quickly get a handle on the essentials, understand why they matter, how they fit into the bigger picture, and really, what problem are they solving?
Exactly. The context is key.
Think of this as your shortcut, maybe, to confidently navigating this whole world of containerization. We'll start by building, a solid foundation, looking at the fundamental commands for managing Docker images and containers.
The basics.
Yeah.
Then we'll scale things up a bit. Look at orchestrating multiple services with Docker Compose. That's a real game changer for complex apps.
Oh, absolutely. Compose is essential.
Then we'll dive deep into how Java developers, especially folks using frameworks like Spring Boot, how they integrate their apps with Docker, using tools like Maven.
Right, the build integration is crucial.
And finally, we'll touch on Docker Swarm for deploying and scaling applications across, like, a whole cluster of machines.
Taking it beyond a single host.
Okay, sounds like a plan. Let's truly unpack this. So to kick things off, let's ground ourselves in the absolute core. Docker, fundamentally, it works with these two main things: images and containers. If you think about it, images are kind of like the blueprints for your software environment, right? They're static, pre-configured snapshots.
Yes, a template.
And containers. They're the live running instances you create from those blueprints.
The actual running process, yep. So when you first open up your Docker environment, what's the very first command a developer probably reaches for? Just to get a clear picture of what's actually there, what's running.
Yeah, that's a great starting point.
Okay.
You need to see what you're working with. The foundational commands here are Docker images, A, that lists all the Docker images you have stored locally. Ones you've pulled, ones you've built, everything.
Gotcha. A for all.
Exactly. And then for containers, Docker eps is your main go-to.
Yeah.
That shows you only the containers that are currently running.
Just the live ones.
Right. But if you need to see everything, maybe containers that stop because of an error or ones you just stop manually, then Docker eps reveals all of them.
Okay, stopped or running.
What's kind of cool here is how quickly these simple commands give you that immediate bird's eye view of your whole container setup, like a dashboard almost.
Yeah, I can see that. Okay, so once you see your containers, you definitely need to manage them. Starting, stopping, maybe even forcefully killing them seems pretty straightforward from our cheat sheet. We see commands like Docker start container name, Docker stop container name, and Docker kill container name. And there's even one for a real clean sweep. Docker kill, Docker PZQ, to take down all running containers.
Whoa. Careful with that one.
Yeah, probably. But what's the practical difference between stop and kill? When would you use one over the other in a real scenario?
Oh, yeah, that's actually a really crucial distinction. So Docker stop, it tries to be polite,
Polite.
Yeah, it sends a sigterm signal first, gives the main process inside the container a chance to shut down gracefully.
Okay, like save its work or close files.
Exactly. Save state, close network connections, that kind of thing. It waits a bit, and if it doesn't stop, then it sends the kill signal.
Yeah.
But Docker kill.
Less polite.
Way less polite. It's just sig kill.
Yeah.
Straight up. Immediately terminates the process.
Like pulling the plug.
Pretty much, yeah. You'd use kill when stop isn't working, maybe the container is unresponsive, or you just need an immediate no-nonsense termination, like for a runaway process or something.
Okay, that makes sense. Treat them like processes you can just terminate.
Exactly. It highlights how Docker treats containers as sort of ephemeral. You spin them up, spin them down. Ideal for microservices or quick tests, not like precious long-running servers you have to coddle.
Right. And once they're stopped, you might not want them hanging around, cluttering things up.
Yeah.
I see commands for removing them. Docker arm container name for stopped containers, and Docker ATAN2Q to clear out all stopped containers in one go.
Another potentially dangerous one if you're not careful.
True. And then for the images themselves, it's Docker Army image name. But what about these dangling images the sheet mentions? Why are they specifically called out for deletion with Docker Army no, Docker images nan EQ dangling true?
Ah, dangling images.
Yeah.
Yeah, that's a good practical point for, like, housekeeping. They're essentially untagged image layers. Think of them as intermediate steps in a build that are no longer referenced by any actual named image.
Like leftover build artifact.
Exactly, like construction debris after you finish building. They're just taking up disk space and aren't serving any active purpose. So that command, Docker Army, Docker images minus Q as strangling true, specifically targets just those unreferenced layers.
So getting rid of them is just good practice for cleanup.
Totally. It keeps your Docker environment lean, saves disk space, and, maybe more importantly, ensures you don't accidentally run some old intermediate image layer you didn't intend to. It's just about keeping things tidy and efficient.
Okay, got it. So you've got your container running, maybe it's acting weird, or you just need to poke around inside, check a log file or something. Our notes mention this command that's not technically SSH, but gives you a bash shell inside the container. Sudo docker exec, a container name bash.
Docker exec.
It's a lifesaver. Yeah, sounds incredibly useful for debugging. How exactly do developers use this beyond just getting a shell prompt?
Oh, all sorts of ways. You're right, it's your window into that isolated container world. Beyond just debugging or checking logs or verifying file permissions, devs use it to, say, quickly install a missing tool temporarily just for testing.
Oh, okay. Without rebuilding the whole image.
Exactly. Or maybe run a specific diagnostic script inside the container to figure out what's wrong. It allows for that kind of on-the-fly inspection and intervention. Saves a ton of time compared to rebuilding and redeploying just to check one little thing.
I can see that. So containers are isolated, but not complete black boxes.
Right. You can peek inside when you need to.
And, okay, let's say you've peeked inside. Maybe you made a quick fix directly in the running container, or you just captured a specific state you want to save. I see you can save that running container state as a new image using docker commit image name for image.
Yep, Docker commit.
That sounds like a powerful way to create custom images really quickly.
It is, and it offers a lot of flexibility, especially for like rapid prototyping, or if you've tweaked a configuration inside a running container and want to quickly save that exact state. You capture everything, the file system changes, the installed packages, whatever you did.
I sense a but.
Wait, yeah. While it's flexible, it's generally considered less ideal for production builds compared to using a Docker file.
Why is that?
Because a Docker file gives you a clear, version-controlled, scripted recipe for how your image is built, step by step. It's reproducible and transparent. Docker commit is more like taking a snapshot. It's harder to track exactly what changed or why.
Ah, okay. So Dockerfile for repeatable production builds, commit more for quick dev debug snapshots.
That's a good way to put it. It also kind of ties into that core Docker philosophy of immutable infrastructure, the idea you build an image and it doesn't change. Updates mean building a new image from your Docker file and replacing the old container. It sort of breaks that mold a little.
Immutable infrastructure. We should probably come back to that thought. Okay, so whether you use commit or a Docker file, when you first run an image, you're not just firing it up, you're often configuring it.
Right.
The cheat sheet highlights these crucial parameters for Docker run SHD to run detached in the background.
Essential for servers.
defb host port.container port for port mapping.
Super important.
defb myvar myprop for setting environment variables.
For configuration.
And defb host path.container path to share storage using volumes. Can you elaborate a bit more on why port mapping and volumes are just so fundamental?
Oh, absolutely. These are the parameters that actually make your containers useful by connecting them to the outside world and managing their data. Take port mapping, the defi flag.
Yeah.
Your container has its own internal network, right? If you run a web server inside on, say, port 8080, nothing outside the container can reach it by default.
It's isolated.
Exactly. TAP2P 80.8088 or whatever ports you choose creates that bridge. It maps a port on your host machine to the port inside the container. That's how users actually connect to your web app. It enables network access.
Got it. The bridge. And volumes. The TAFV flag.
Volumes are critical for anything involving persistent data. Remember, containers are often ephemeral. If you stop and remove a container, any data written inside its file system is usually lost.
Gone.
But if you use -myHostData.app data, again, example paths, you're telling Docker, hey, this app data directory inside the container actually store its contents in the myHostData directory on the host machine.
So the data lives outside the container.
Precisely. So even if you remove and replace the container, maybe to update the application code, the data in that volume persists. Think databases, user uploads, logs you want to keep, configuration files, anything that needs to outlive the container itself.
Okay, that makes total sense. Port mapping for access, volumes for persistence, really core concepts. So if one container is powerful for packaging, say a single microservice, what about a bigger application? One that's built from, I don't know, 10 or 20 separate services all working together, a web front end, some back-end APIs, a database, maybe a cache.
Yeah, modern apps get complex fast.
That's where Docker Compose comes in, isn't it? It lets
Well,
you
yeah.
define and run these multi-container Docker applications. What's the biggest headache Compose solves compared to trying to juggle all those containers manually?
Oh, it solves a massive headache. Imagine trying to manually start each of those services you just listed using individual Docker run commands. You need to remember all the flags, set up a network so they can talk to each other, manage dependencies like making sure the database starts before the application.
Yeah, that sounds like a nightmare. Error-prone.
Totally. Docker Compose simplifies all of that. You define your entire multi-service application, stack all the services, their images, networks, volumes, dependencies, ports, everything in a single YAML file, usually called docker-compose.yaml.
One configuration file to rule them all?
Pretty much. The biggest headache it eliminates is that orchestration complexity. With Compose, you just run one command, docker compose up EAB, and it brings your entire application stack to life in the right order, all connected, running in the background.
That is a huge simplification. And our cheat sheet highlights the core commands for Compose, Docker Compose build to build the images defined in the file, and Docker Compose up at AD to start everything.
Yep, those are the main ones.
But what's fascinating is the mention of this force recreate flag used with Docker Compose up AD. The source specifically notes a real-world problem it solves. I was deploying a Spring Boot web application from Jenkins and found the Docker container was not getting refreshed with the latest Spring Boot artifact. Can you elaborate on why that happens and how this flag is the fix?
Yes. The classic caching problem. Especially in CI/CD pipelines, it's super common. Docker Compose, by default, tries to be efficient. If it sees a container for a service already exists, and the configuration or image name hasn't changed in your docker compose.iml file, it might just start the existing container instead of creating a new one.
To save time.
Right. But the problem is, maybe your Jenkins build created a new version of your Spring Boot JAR file, but you pushed it using the same Docker image tag, like myapp.latest. Compose looks at the tag, sees latest, thinks, oh, I already have latest, and doesn't pull the potentially updated image or rebuild the container.
So you end up deploying the old code.
Exactly. The force recreate flag tells Compose, nope, don't reuse anything. Tear down the existing containers for these services and create completely new ones, making sure you pull the absolute latest image version or use the latest build context. It forces a refresh.
Okay, so it bypasses the cache and ensures you get the truly latest artifact.
Precisely. It's a small flag that solves a big, frustrating headache for ensuring consistent deployments, especially from automated systems like Jenkins.
That's invaluable. It looks like Compose also gives you a sort of standard workflow for updates. The sheet lists this sequence: Docker Compose stop myzt1, then Docker Compose arm ashf, then Docker Compose pull, Docker Compose build, and finally Docker Compose uppity.
That's a very common pattern for doing a full update.
It looks like a pretty methodical way to make sure you're always working with fresh, updated images and clean containers.
It is. It's a robust cycle. Stop myzt1 tries a quick, graceful shutdown. RMM-F forcefully removes the old containers. Pull grabs the latest base images from your registry. Build rebuilds any images defined locally in your Compose file using the latest code. And up.d starts the new set.
Ensures everything is fresh.
Yeah, prevents weird issues from stale caches or leftover container state. It's a good, clean way to redeploy your stack.
And for keeping an eye on this whole orchestra once it's running, the sheet also covers logging. Docker Compose logs-f to follow the combined logs of all the running services.
Which can be noisy sometimes.
I bet. Or Docker Compose logs service name to just follow the logs from one specific service.
Yeah, much more targeted.
It really feels like Compose is the conductor, making sure all the different pieces start correctly, run together, and you can still listen in on each one individually if you need to.
That's a great analogy. It really does orchestrate the whole thing.
Okay, now our cheat sheet is explicitly called Docker for Java developers. So let's pivot a bit and focus on some of the Java-specific stuff. I see some very detailed steps outlined for actually adding Java, specifically Oracle Java, to an image using a Docker file. What's the key takeaway there for a Java dev building their own custom image?
Right. This section gets very practical if you're not just using a pre-built Java image, but need to construct your own environment, maybe for compliance reasons, or needing a very specific JDK version.
Like needing Oracle JDK specifically.
Exactly. The example is for CentOS RHO. It shows setting environment variables like Java version, build version, good practice for clarity and managing versions. Then it uses standard Linux package management, yum upgrade, yum install, reget. But the really crucial part is how it downloads the Oracle JDK RPM using reget.
How so?
It uses a specific header, do get and no check certificate, no cuckoo's header cookie. Oracle license accepts secure backup cookie. That Oracle license accepts secure backup cookie part is key.
Why is that header needed?
It's Oracle's way of requiring you to programmatically accept their license agreement for automated downloads. Without it, the download would probably fail in a script. It's vital for making the image build repeatable and automatable, especially in CI/CD.
Ah, okay. Handling the license acceptance automatically.
Then it's about installing that downloaded RPM and, importantly, using the alternatives command to configure the system to use that specific Java version for the Java, Javas, and Java commans.
So the system knows which Java to use if multiple are installed.
Precisely. The key takeaway is the meticulousness required. Building a custom runtime environment in a Docker file demands precision at every step. Version numbers, download methods, system configuration to guarantee your Java app gets the exact, consistent environment it expects every single time it runs, no matter where.
That level of detail really hammers home the reproducibility benefit of Docker. Okay, so Java is installed in the image. Now, how do you get your actual Spring Boot application, that executable JAR file, into the image and make it run automatically when the container starts? Because that's the main event, right? Running your app.
That's the whole point, yeah. The sheet shows a pretty standard but critical set of Docker file instructions for this. First, something like add maven myapp -0.1 snap awk shashi.jar myapp.jar.
Copying the JAR in.
Yep, copies the JAR built by Maven or Gradle from your build context into the image, renaming it to myapp.jar for simplicity. And there's often a run myapp.jar.
Why the touch command?
Sometimes it's used to ensure the file exists with correct permissions or to update its timestamp, which can occasionally help with certain caching layers or file system behaviors inside containers. It might not always be strictly necessary, depends on the base image and context.
Okay, but the most vital part is
the entry point command. Usually something like entry point, Java, java.security.egd file.dev.yourrandom, jar, myapp.jar. This is the command that Docker will execute when the container starts.
So it's literally running Java jar on your application JAR.
Exactly. And that deji java.security.egd file.d.yourrandom part, that's a common JVM argument, especially for Spring Boot apps running in containers.
What does it do?
It points Java's secure random number generator to a source of entropy, div-random, that's usually faster inside containers, which can significantly speed up application startup times, particularly for things involving cryptography or secure sessions.
Oh, interesting. A performance tweak for containers.
So putting it all together, these instructions package your compiled application, JAR, and its Java runtime environment, plus any specific configurations like that docd flag, into one self-contained portable unit.
Finally solving the, well, it works on my machine problem.
That's the dream. Consistent environments everywhere.
It definitely makes deployment cleaner. But it also looks like you don't have to run Docker commands separately. You can integrate Docker right into your Java build process using Maven. Our notes mention the Fabric 8 Maven plugin.
Yes. This is where things get really smooth for Java developers. The Fabric 8 Maven plugin, and there are others too, like Jib from Google, lets you manage the Docker image lifecycle directly from your Maven build.
How does that work?
The cheat sheet lists several goals you can run with Maven. MVN docker.stop to halt containers managed by the plugin. MVN clean package docker.build is a common one. It cleans, compiles your Java code, packages it into a JAR, and then builds the Docker image all in one command.
Okay, that's slick. Code to container in one step.
Totally. Then you've got MVN docker.push to publish that newly built image to a registry, like Docker Hub or a private one, and MVN docker.start or MVN docker.run to actually start containers based on your images right from Maven.
Wow. That gives Maven a lot of control over Docker.
It really does. It means a Java developer might just need to know their Maven commands, and the plugin handles the Docker interactions under the hood. It massively streamlines the workflow, especially for local development loops and integrating into CI/CD pipelines.
And the configuration for this Fabric 8 plugin in the pom.xml file looks pretty powerful too. I see examples of defining runtime parameters using image run tags, mapping ports with ports port 80.8080 ports.
It's like gas flag.
Specifying environment variables with end tags, and even linking containers using link. It seems like almost anything you can do with Docker run on the command line, you can configure right there in your Maven pom.xml.
Exactly. And that centralization is a huge win. Instead of having Docker flags scattered in shell scripts somewhere, your container's runtime configuration lives right next to your application's build configuration.
Consistency again.
Absolutely. It ensures that every time the Maven build runs, the Docker image is built and configured in exactly the same way. But this does raise an important practical question, doesn't it?
Which is?
If you're using mvn docker.push to push images, especially from an automated CI server, how do you handle your Docker Hub or other registry credentials securely? You definitely don't want to put your password in the pom.xml.
Oh, right. Good point. How do you do that?
The sheet provides the standard Maven answer. You store them in your .m2 settings.xml file. You create a server entry with an EID that matches the registry, like docker.io for Docker Hub or whatever ID you configure in the plugin, and put your username and password there.
And Maven just picks it up securely.
Yep. Maven knows to look in settings.xml for server credentials based on the ID. It keeps your sensitive info out of your project's source code, which is crucial for security and automation.
Okay, that's a critical piece for making the Maven integration work securely in pipelines. All right, so we've covered single containers, we've done groups of containers with Compose, we've even integrated Docker right into the Java build with Maven. But what happens when you need to run your application across, like, multiple servers, not just one machine? That's where Docker Swarm fits in, correct? Taking orchestration up a level.
Exactly. Docker Swarm is Docker's native solution for clustering and orchestration. It lets you manage a group or swarm of Docker nodes, physical servers, virtual machines, as if they were a single unified system.
So you can deploy and scale apps across many machines.
Precisely. It provides high availability, load balancing, and fault tolerance. What's kind of interesting, though, is that it's not on by default. It's an opt-in feature within Docker Engine.
So you have to explicitly turn it on.
Yeah. You initialize the swarm on the first machine you want to act as a control center using Docker Swarm init. That node then becomes the first manager node of the swarm.
And the sheet mentions different node types, manager and worker. Can the manager nodes also run application containers, or are they purely for control?
That's a good question and an important distinction. Manager nodes can actually run application containers, tasks, by default, unlike some other orchestrators where managers are strictly control plane.
Oh, okay.
However, the cheat sheet rightly points out that the swarm management commands like deploying services, managing nodes, can only be executed from a manager node. Worker nodes exist purely to execute the tasks assigned to them by the managers.
Got it. So how do you add more machines to the swarm, like make them workers?
Once the swarm is initialized, a manager node can generate a join token. You take that token and run a command on the machine you want to add, something like Docker Swarm, join token, the long token string manager, that IP.port.
And that token is the security mechanism.
Yeah. It ensures only authorized nodes can join the swarm. You can get the specific token needed for workers using Docker Swarm join token worker on a manager. There's also a separate token for adding more managers for high availability of the control plane itself.
Makes sense. So once you've got the swarm running, maybe a few managers, a bunch of workers, how do you actually see what's deployed and running across all these different machines? Docker Ops won't cut it anymore, right?
Right, because you're now managing things at a higher level, the level of services. A service is like the blueprint for your application running on the swarm, defining which image to use, how many replicas, containers you want, network settings, ports, etc.
So you manage services, not individual containers directly?
Mostly, yes. You'd use Docker Service Hills to list all the services currently running on your swarm.
Okay.
Then, if you want to see the individual container instances for a specific service, which Swarm calls tasks, you'd use Docker service name. That shows you which tasks are running, which node they're on, and their status.
Ah, okay. Service roles for the overview, service apps for the details of one service.
Exactly. And to see the nodes themselves, their status, ready, down,
right,
and their role manager worker, you use Docker nodals.
That gives you the cluster health view.
And this naturally leads to managing those nodes. What if you want to promote a worker to be another manager for redundancy, or demote one, or remove a machine that's being decommissioned?
Yeah, how do you do that?
The sheet shows the commands. Docker node promote node name to make a worker a manager. Docker node demote node name to do the reverse. And Docker node add for node name to remove a node from the swarm entirely.
Pretty straightforward. And removing a whole application.
You just remove the service definition using Docker service name. Swarm then handles stopping and removing all the tasks, containers associated with that service across the cluster.
Cool. It seems like that concept of port mapping -p host port .container port is so fundamental it even shows up here in the swarm section when defining services.
It really is. When you define a service in Swarm, you still need to publish ports so that traffic coming into any node in the swarm can be routed correctly to a container running that service, even if that container is on a different node. Swarm handles that routing mesh automatically.
So that basic RAPU concept scales all the way up.
It's core to making containerized services accessible, whether it's one container or 1,000 across a cluster.
Wow, okay. That was definitely a deep dive into Docker, especially through that Java developer lens.
Yeah.
We went from the absolute basics, images, containers, Docker access, understanding things like graceful shutdowns versus killing,
The stop versus kill.
all the way to orchestrating complex multi-container apps with Docker Compose, handling those tricky caching issues with Force Recreate.
Yeah, the CI/CD helper.
Then we look at the specifics for Java, building custom JDK images, getting Spring Boot apps running with the right entry point, and even integrating everything smoothly into the Maven build process using plugins like Fabricate.
Bridging the Java world and the container world.
And finally, scaling out beyond one machine with Docker Swarm, understanding managers, workers, services, and tasks. We really extracted a lot from that cheat sheet, I think. Not just the what, but the why.
Absolutely.
Yeah.
This whole journey through the cheat sheet, it really just highlights how Docker empowers developers, doesn't it, to package things up, distribute them reliably, run them consistently wherever.
Yeah.
That ability to quickly manage all the processes, dependencies, configurations, and then scale it all up or down, it's truly transformative for how we build and deploy software today.
Yeah.
It takes away so much friction.
So for you listening, what does this all mean? Well, getting a handle on these Docker commands and concepts, it's really more than just learning syntax, isn't it?
Oh, definitely.
It's about gaining this incredibly powerful tool set for modern software development. The consistency, the portability, the efficiency Docker brings. It can genuinely streamline your workflows, make your deployments way more reliable, and just make scaling applications much, much more manageable.
Whether you're a solo dev or on a huge team.
Yeah. It fundamentally changes how you approach getting software from your laptop into production.
You know, we spent a lot of time on the commands, the practical how-to.
Yeah.
But thinking about it, especially when we talked about Docker commit versus Docker file and avoiding stale deployments with Compose, it all implicitly points back to that underlying philosophy we touched on, immutable infrastructure.
Right. Build once, don't change it, just replace it.
Exactly. The idea that you don't patch or modify running containers. You build a completely new image with the update, deploy new containers from that image, and then tear down the old ones.
A different way of thinking about updates.
It is, and it makes you wonder, beyond all the obvious benefits of consistency and easier rollbacks that come from these commands, how much does adopting this purely immutable approach really change how we have to think about system design, state management, or even debugging in really complex distributed systems? Are there new challenges that arise precisely because everything is treated as disposable and replaceable?
That's a really interesting thought to chew on. The deeper implications beyond just the commands themselves. All right, that's all the time we have for this deep dive. Until next time, keep exploring.